So in the post midterm part of this course, we will look at a large number of applications of quantum mechanics. Especially I will just outline the applications that we will study up till the final exam. We will look at the hydrogen atom. You see, the hydrogen atom is the simplest atom you can ever think of. It's an electron circulating, or an electron outside a nucleus. And we've already seen why the electron cannot exist inside the nucleus. The uncertainty principle prevents this. And why doesn't the electron shoot away from the atom, from the nucleus? Classical physics tells us that the atom has to be unstable, because the electron is accelerating, it's continuously emitting radiations, so it must spiral down into the nucleus. But why are atoms supremely stable objects? Atoms are stable, that's why the universe exists. Otherwise we cannot exist, animals cannot exist, plants cannot exist, life can't exist, planets cannot exist, nothing can exist if atoms are unstable. So we already have an idea of why atoms are unstable. But the simplest of all the atoms is hydrogen. And hydrogen is about 99% of the universe. Now, what is the hydrogen atom, and what are the energy levels of the electrons inside the hydrogen atom, whether it's a bound system or an unbound system? And the hydrogen atom is the simplest atom, but it's not easy to understand. So this is the richness of nature, that even the simplest objects are very hard to understand and understand completely. What is the next most complicated atom after hydrogen? Helium? Or it could be deuterium as well. Alright, let's consider helium. Now helium has 2 electrons, and the normal isotope of helium has 2 protons and 2 neutrons. Solving the quantum mechanics for helium atom is extremely difficult. देखिए, हाइड्रोजन के बाद सीढ़ी का अगला कदम है हीलियम. अब हाइड्रोजन सॉल्व हो जाता है आसानी से, आप कागज पे करेंगे, हम ब्लैक बोर्ड पर करेंगे, इट इज सॉल्वेबल. बट हीलियम, which is the next most complicated atom, and it's number 2 in element number 120. यानी कि सिंपल होना चाहिए, लेकिन हीलियम एटम भी हमारी 10 तरह से हमारी पहुंच से बाहर हो जाता है. उसको कंप्लीटली एनालिटिकली सॉल्व करना, तो फिर हमें एक मशीन इस्तेमाल करनी पड़ती है जिसको कहते हैं कंप्यूटर. फिर हमें कंप्यूटर का सहारा लेना पड़ता है कि हम हीलियम एटम को सॉल्व कर सकें, लिथियम को सॉल्व कर सकें. अभी ये सिंपल एटम्स हैं, यानी कि नेचर इतनी कॉम्प्लिकेटेड है, लेकिन जहन भी है हमारे पास, और हमसे बेहतर जहन भी थे जिन्होंने क्वांटम मैकेनिक्स की बुनियाद रखी. तो उन जहनों ने हमें बताया कि हम हीलियम एटम को कैसे स्टडी कर सकते हैं, लिथियम को कैसे स्टडी कर सकते हैं. लेकिन हमारा फोकस होगा हाइड्रोजन एटम पर. और फिर जब हम एटम की बात कर चुकेंगे, वी लुक एट मॉलिक्यूल्स. हाउ डू मॉलिक्यूल्स फॉर्म? बिकॉज एटम्स बॉन्ड टुगेदर to form molecules, so we will look at bonding. And when we study the hydrogen atoms, we will understand what is meant by orbitals. Now orbitals is an extremely important concept. You've studied about orbitals in chemistry. I will try to give you a different taste of orbitals than what you've studied in chemistry. I will try to give you a complete fundamental physical mathematical picture of orbitals. What is an s orbital really? What is a p orbital? What is a d orbital? And by the concepts that you've learned so far in quantum mechanics and the Schrodinger equation, it will not at all be difficult to understand what orbitals are. Then we will study about the hydrogen atom, we'll study about molecules, and then we will study about solids. So how do solids form? What is a semiconductor? What is a conductor? An insulator? A superconductor? Why does iron attract a magnet? Why does magnet attract iron? And then we will look at some exotic applications. For example, we will look at spintronics. What is spin? And I will try to give you a flavor of quantum computing. So these are the different applications of quantum mechanics that we will be studying up till our final exam. But today I would like to touch upon the concept of quantum mechanics in 3 dimensions. So far what we've learned is the infinite well problem in 1 dimension. That is, we have a well, the potential energy is 0 inside the well and it approaches infinity outside a well. The well is of a finite length. So what happens inside the well? What about the energy states inside the well and the wave functions? What is if you solve the Schrodinger equation for this potential energy, what are the wave functions like? The wave functions are, they are sine waves, they are standing waves, sine waves with nodes at the walls, because the potential energy is going to infinity. So you have a fundamental wave, a first harmonic, a second harmonic, and so on. And the energy becomes quantized. So E is quantized. Correct? So you have an energy E naught, you have an energy 4 E naught, N 9 E naught, and so on. So the energy varies as the square of an integer. The energy depends upon N and is given by N square, H bar squared, pi squared over 2m L squared. So the energy is quantized. Now I would like to ask you the question, where is this quantization coming from? Please raise your hands. What is the origin of this quantization? कोई और? ये क्वांटाइजेशन कहाँ से अपीयर हो रही है? तो exactly, there have to be nodes at the boundaries. That is, this is a bound problem, bound system. It's a bound system, and when we impose these boundary conditions, the wave function has to disappear in this region. It's not a finite well, it's an infinite well. The wave function has to disappear in this region and it has to disappear in this region. Therefore, since the wave function has to be continuous, therefore at the walls the wave function must be 0. And if the wave function is 0, that imposes certain constraints on the wave number, and it imposes certain constraints on the energy, and the energy turns out to be quantized. Now you solve this problem in detail, and remember the golden words: localization leads to quantization. Since we are localizing the particle, we are constraining the particle to exist in a certain length, and it cannot exist outside this well. It's an infinitely deep well, and the particle has to remain inside this well for all times to come. So the energy of this particle is quantized. This is the ground state. It can go to the first excited state, to the second excited state. If it makes transitions between states, it absorbs or emits photons. So if you have a linear molecule, for example a DNA molecule, and an electron is trapped inside the DNA molecule, and you approximate the DNA molecule by a linear molecule, the electron is confined to exist within the length of the molecule. Suppose there are 100 base pairs, so the electron can traverse 100 base pairs inside the DNA molecule. So that is like an infinite well, and the energy of that electron will be quantized inside the well. You have linear polymer chains. An electron is put on a polymer chain. The energy of the electron is quantized in this fashion. But this is a one-dimensional problem. It's a somewhat artificial problem, and we studied it because It gives us the convenience of being able to solve it. Most problems in real life are three-dimensional. Notice the appearance of this this quantum number n. ये quantum number जो है ना n, ये define कर रहा है wave function को भी और energy को भी. ठीक है? तो एक integer, an integer is appearing, and the integer is appearing out of the wave nature of a particle and imposing the boundary conditions. Remember the golden words always: localization leads to quantization. तो अब ये quantum number एक ही quantum number है n, and n is taking up values. What is the smallest value of n? 1, 2, 3 and so on. Why can't n be 0? Because then the wave function will be 0, the particle does not exist. And corresponding to different values of n, we can write the wave function as well. The wave function, if you recall, is given by a normalization constant a sine of n pi x over L. This is the wave function. So you can identify the wave function by the quantum number as well, n. And there is only one variable x because it's a one-dimensional problem. And we also know that k, the wave number, is given by n pi over L. So this is kx or kn. The wave number is quantized as well, and hence the momentum is quantized. And n defines the energy, it defines the momentum, it defines the wave number, it defines the wave function as well. Can you find A? A can be found by the normalization condition. So this is a review of what we studied so far. Energy becomes quantized, the momentum becomes quantized. Now how do we extend this problem to our real life? Is the hydrogen atom a one-dimensional system? No, it's a three-dimensional system. So how do we look at the problem in 3 dimensions? Okay, one question. Corresponding to one energy, how many wave functions exist? एक ही wave function है, एक यानी 1-to-1 correspondence है wave function और energy के दरमियान. 1-to-1 correspondence, एक wave function की एक energy. If the electron possesses a certain wave function, it has a certain energy. Another wave function, another energy. So keep this in mind. There's a 1-to-1 correspondence between the wave function and the energy. Now let's extend this problem to 3 dimensions and see how we can solve the Schrodinger equation in 3 dimensions with a simple example. Suppose these are our axes, x, y and z. Now I define a region in this 3-dimensional space which is of the form of a cube. Now this is a cube, each side has a length L. What is the next step? The next step is defining the, in order to solve the Schrodinger equation, we need a form of the potential energy. What's the potential energy? Inside the cube, the potential energy is 0. Inside this cube. And outside the cube, everywhere, the potential energy is infinite. In order to answer this question, we'll have to wait till we... You see, it comes out of the mathematics. You get a wave function, you solve the Schrodinger equation, the differential equation, you get a wave function, and corresponding to this wave function there is one energy. Now we will see that this is not the case in the 3 dimensions, and we will, when we understand this, you'll get a better answer. But you understand the physical system now. कि पोटेंशियल एनर्जी की क्या फॉर्म है. See, inside now we have a 3-dimensional well. एक कुआं है जो 3 dimensions में एग्जिस्ट करता है. ठीक है, एक छोटा सा बॉक्स है, यानी अगर ये एक क्यूब है, ये क्यूब तो नहीं, ये तो पैरेललेपिपेड है. वाकई अब लफ्ज़ ही ऐसा है, क्या करें. अब ये पैरेललेपिपेड है, इसके अंदर पोटेंशियल एनर्जी 0 है और इसके इर्द गिर्द पूरी यूनिवर्स में पोटेंशियल एनर्जी इन्फिनिट है. So the particle can only exist inside this well, because outside the well its potential energy is infinite. Therefore the wave function of this, the 3-dimensional wave function of this particle can only be non-zero inside this parallelepiped. ठीक है, it has to be 0 everywhere outside. Now what is this 3-dimensional wave function and what are the quantum numbers? Now, this is a real problem.
Can we reduce this cube to a quantum dot?
That is a 0-dimensional system. बिल्कुल. Can have a 2-dimensional system which is a sheet. We can have a quantum wire. So we're looking at the 3-dimensional problem now. So how do we solve the Schrodinger equation? First of all, we should remember that we wrote the Schrodinger equation in 1 dimension. And the 1-dimensional Schrodinger equation, the complete form is given by minus h bar squared over 2m partial squared partial x squared, a wave function which depends upon x and time. मैं टाइम डिपेंडेंट की भी पहले बात कर रहा हूँ, ठीक है, प्लस u ऑफ x, ये पोटेंशियल एनर्जी टाइम पे डिपेंड नहीं कर रही, और वेव फंक्शन x एंड टाइम आयोटा h बार now this is our 1-dimensional equation. How is this modified in 3 dimensions? First question, can we derive this equation? No, we cannot. It's a fundamental fact of nature. And how do we know it's correct? By working out the wave functions, by working out the corresponding energies, and it matches, exactly matches our experimental observations. That is, whenever transitions take place between levels, you get photons of the correct frequency, and you can measure the frequency of photons. Now, how does this problem change if we move from 1 dimension to 3 dimensions? First of all, we know that in 3 dimensions, I don't know why this is running all the way up, you have a point in 3 dimensions. Instead of x, we have x, y and z. So the wave function psi now depends upon, instead of 2 variables x and t, depends on 4 variables. You have x, y, z and t, and your potential energy also depends upon 3 variables, depends upon x, y and z. The derivative with respect to time remains unchanged. Now what about partial square over partial x squared? In 3 dimensions, no, not r square. We're talking about x, y and z's. We're talking about the Cartesian coordinates. In 3 dimensions, instead of this has to be replaced somehow by, we cannot be prejudiced towards x. We need to have a y term, we need to have a z term as well. Okay? So we have to replace this differential operator by partial square partial x squared plus partial squared partial y squared plus partial squared partial z squared. Okay? So let's write the Schrodinger equation in 3 dimensions now. In 3D, the Schrodinger equation becomes minus h bar squared over 2m x y z time plus u x y z So this really is the Schrodinger equation in 3 dimensions, and this particular operator is a differential operator. This particular object is given a special symbol, okay, and that symbol is, since this is a definition, I write 3. This symbol is, the symbol is nabla. सिंबल को नैबला कहते हैं, लेकिन इस पूरी चीज को लैप्लाशियन कहते हैं. यानी सिंबल अल्फाबेट नैबला है, नैबला उल्टा डेल्टा. अगर डेल्टा लफ्ज कहां से आया? ग्रीक है. क्यों है ये डेल्टा? क्या कहां से आया डेल्टा लफ्ज? पानी का डेल्टा होता है. वो क्या होता है डेल्टा? जी अल्फाबेट डी है. तो डेल्टा का ओरिजिन क्या है लफ्ज का? जब ग्रीक्स मिस्र पर हुकूमत करते थे, ठीक है, आपको पता है ग्रीस और मिस्र में कुछ ज्यादा फासला नहीं है, इट्स ओनली द मेडिटेरेनियन सी इन बिटवीन. तो जो दरियाए नील जब समंदर में गिरता है, देखिए दरियाए नील जुनूब साउथ से नॉर्थ की तरफ फ्लो करता है, दरियाए सिंध नॉर्थ से साउथ की तरफ, दरियाए नील सूडान से निकलता है और मेडिटेरेनियन सी में फॉल करता है. तो जब दरियाए नील समंदर के पास पहुंचता है तो वो बहुत सी शाखों में बट जाता है और एक डी शेप का वो बनाता है, यानी बहुत सी शाखों में बट के फिर वो समंदर में गिरता है. तो दैट इज लाइक एन इन्वर्टेड डी, एंड दैट इज व्हाई इट इज कॉल्ड अ डेल्टा, बिकॉज द ग्रीक्स गेव इट द नेम डेल्टा. So this is an inverted delta. It's called a nabla, and this operator as a whole is called a Laplacian. Laplace भी आपको पता है एक फ्रेंच इंजीनियर था. Now, so we can replace this operator by a Laplacian, by this symbol delta squared. And this delta square must, this is a predator, it must have a prey, and this is the prey. ठीक है, ये ऑपरेंड है, ये किसी चीज पर एक्ट होगा, ठीक है ना. जिस तरह इस ऑपरेटर के साथ एक ऑपरेंड आना चाहिए, लाइकवाइज दिस मस्ट हैव a wave function to the right of itself so that it can act on the wave function. So this is the 3-dimensional Schrodinger equation. Is it time dependent or time independent? Time dependent. Now we already know, we've learned about problems in 1 dimension that we can make a time independent equation out of it. We can make a time independent equation out of it, and that is by simply replacing this wave function, writing this wave function as a product of a spatial part and a time dependent part, right? We've already learnt about this. And when can we write, when is it possible to write this decomposition? When? Exactly, when the potential energy does not change with time. ठीक है? Or the energy remains constant. So the potential energy does not change with time. We can make this substitution, insert the values into the 3D equation and we learn that this time dependent part is simply exponent minus iota the energy T over h bar. This is the time dependent part, and the time independent wave function obeys a time independent Schrodinger equation, which is minus h bar squared over 2m del squared nabla squared or the Laplacian operator, only the space dependent part, plus u x y z, only the space dependent part. What do I write here? The energy. So this is our time independent Schrodinger equation in 3 dimensions. Now this is our time independent Schrodinger equation. We have to apply this equation to our 3-dimensional problem, which has disappeared again. Here. ये देखें, इस पे अप्लाई करना है. अब आप मुझे बताएं हाँ कि बाउंड्री कंडीशंस क्या है हमारे पास. हाँ बताओ, what are our boundary conditions? What do we already know about the wave function without solving it? कोई नहीं, जरा हौसले से तमाद से बात करो. क्या हो गया बताओ, बहुत आसान है जी. क्या जीरो होगा? क्या जीरो होगा? वेव फंक्शन जीरो होगा कहां पर? when x is equal to or greater than L, when y is greater than or equal to L. ठीक है. so for x, y or z, either one of them greater than or equal to L, or x, y, z, either one of them smaller than or equal to 0, the wave function is, क्या है वैल्यू वेव फंक्शन की? 0, because the wave function has to disappear outside the quantum well, outside the 3-dimensional well. Therefore at the walls at x equals 0, any y, any z, the wave function is 0. ठीक है. Likewise, the wave function at any x, y equals 0, any z is 0. The wave function at any x, any y, z equals 0 is 0. The wave function at x equals L, any y, any z is 0. So you have 6 boundary conditions. ठीक है. यानी wave function यानी इस पैरेलल पेपर की कितनी वॉल्स हैं? 6. On the 6 walls of this well, the wave function has to go to 0, because the wave function is 0 outside the well, and the wave function has to be continuous, so it has to be 0 on all 6 of the walls. ठीक है. So these are our boundary conditions. I've written only one of them. So these are our boundary conditions, and inside the well what is the potential energy? 0. U is 0. So our equation becomes minus h bar squared over 2m del squared So we have to solve this equation respecting these boundary conditions. इन बाउंड्री कंडीशंस को पूरी तरह लिहाज रखते हुए हमें इस इक्वेशन को सॉल्व करना है. एंड दिस इज नॉट अ वन डायमेंशनल इक्वेशन, इट्स अ 3 डायमेंशनल इक्वेशन. तो एक हमें ट्रिक हमें कुदरत ने बता दिया है डिफरेंशियल इक्वेशन को सॉल्व करने का. वो ट्रिक क्या है? सेपरेशन ऑफ वेरिएबल्स. We suppose that our wave function, which depends upon x, y and z, is a product of a function which depends only on x, only on y, a function only on y, and a function only on z. So we make this assumption and substitute this wave function into the time independent Schrodinger equation. Now I give you some time to actually, you will get 3 differential equations. Can you find out what those differential equations are? Just make this substitution. इस substitution ये करें और देखें what do you get.
So क्या ये functions की substitution?
You replace this wave function by a product of 3 wave functions.
रिप्लेस कर दिया, हमने क्या करना?
देखो ना एक्ट हो रहा है ये, इसको ये देखो ये क्या है?
ये नेबुला ऑपरेटर है.
क्या है?
ये सर इन तीनों के पास से ले लेंगे. और एफ के लिए इस तरह और जो होगा उसके इंटरवल.
हाँ
इसी तरह
इस तरह. हाँ अब आगे पार्शियल स्क्वायर लेकिन गलती की है आपने, तो सोचो.
सारे इनको वेरिएबल्स को करेंगे विद रिस्पेक्ट टू वही डिफरेंशियल डालना.
गलती की है आपने, जरा सोचो.
तो सबके साथ ही
सबके साथ है. मैं देख रहा हूँ आप सब लोग एक ही गलती कर रहे हैं. पार्शियल डेरिवेटिव को समझें कि पार्शियल डेरिवेटिव है क्या. व्हेन यू टेकिंग द पार्शियल डेरिवेटिव विद रिस्पेक्ट टू x, g and h are to be treated as constants. You cannot ignore them.
एक्सप्रेशन आपने यहाँ पर एक्स स्क्वायर वाई स्क्वायर जो लैप्लासियन आपने लिखे उसको पार्शियल स्क्वायर और पार्शियल आर स्क्वायर क्यों लिख सकते हो?
इतना सिंपल नहीं है. मैं आपको बताऊंगा कि पार्शियल आर स्क्वायर नहीं है ये.
लेकिन अगर बेसिक 3 डायमेंशन में देखें तो आर पे डिपेंडेंस है उसका.
हाँ हम 3 डायमेंशन में लिख सकते हैं ऑपरेटर, लेकिन वो 1 ओवर आर स्क्वायर नहीं होगा. पार्शियल ओवर पार्शियल आर स्क्वायर नहीं, वो डिफरेंट होगा. मैं आपको बताऊंगा वो क्या होगा. शाबाश. ठीक है, अब राइट हैंड साइड पे भी लिखो ये, और दोनों साइड्स को FG8 से डिवाइड कर दो. Do you get this expression? I've just suppressed G depends upon X, Y, H depends upon Z. So there are small G dependence on Y, H dependence on Z, but I have not bothered writing this dependence every time. So this is the expression that you should get. Remember that when we are taking the partial derivative with respect to x squared, G and H don't disappear. They must appear as constants. Now this is the time independent Schrodinger equation with this substitution. Now simply what you could do is divide both sides by FGH. Divide both sides by FGH. All right, आप यहाँ तक पहुँच गए? Are you with me on this?
Yes, sir.
The right hand side, जी. At this stage we can write this as a normal derivative as well. Yes, at this stage we can replace this partial derivatives with normal derivatives as well. बिल्कुल आप यहाँ डी स्क्वायर एफ और डी एक्स स्क्वायर भी लिख सकते हैं यहाँ पे इस स्टेज पर. शाबाश. अच्छा अब बताओ राइट हैंड साइड कांस्टेंट है? डज इट डिपेंड अपॉन एक्स वाई और जी? नो. E, we are talking about stationary states. Stationary states means E is constant. For a given energy, what is the wave function? Okay, E is a constant. Now when E is a constant, we have a constant on the right hand side and we have a function on the left hand side. This part, does it depend upon any variable? Yes, it depends upon X. Does this depend upon any variable? Yes, it depends on Y. And this depends upon Z. Now we have an X dependence function and a Y dependent function, a Z dependent function. We are adding all three of them and getting a constant every time. What does this mean? This means that this should not depend upon X. And this function should not depend upon Y. And this function should not depend upon Z. So each one of these has to be equal to a constant. So this means that minus h bar squared over 2m 1 over f, which is a function of x. Now I write d square f, which is a function of x over dx squared. This must equal a constant c1. One over g, which is a function of y, d squared capital G, which is a function of y, dy squared is equal to another constant c2. This equals another constant c3. And is there any constraint on the constants? Their sum must equal E. Given this condition, C1 plus C2 plus C3 must equal E. So from one differential equation, which is a three-dimensional equation, we get 3 differential equations and each one of them is one dimensional. देखो ये one dimensional equation है ना, it only depends on x, this only depends on y, this only depends on z. तो separation of variables technique का कमाल ये है कि एक higher dimensional equation को छोटी first order differential equations में बदल देती है, but the number of the first order differential equations is equal to the number of dimensions. So from one 3-dimensional equation you are getting 3 1-dimensional equations, and we can solve 1-dimensional equations easily. So for example, all 3 of these equations are similar, very similar. Can you solve only the first one of them? इस first equation का क्या solution होगा? I give you some time to write down the solution for it. Solve for f. शाबाश. Right? So this is the first equation. First equation में थोड़ी सी rearrangement की इस तरह लिख लिया. Question. In order to simplify things, I would like to ask you a question. Now the question is, उधर माइनस था, राइट लेफ्ट हैंड साइड पे ले गया, प्लस हो गया, थोड़ा सा रीअरेंज किया. Question. I would like you to tell me what are the dimensions of C1. अब मैं जिससे पूछूं C1 की dimensions क्या हैं? Dimensions क्या हैं C1 की? आप बताइए C1 की क्या dimensions हैं? डायमेंशंस का पता है? आप बताइए. यहां किसी को पता है C1 की डायमेंशंस क्या है? क्या हो सकती? जूल्स तो यूनिट्स हो गए ना. एनर्जी. C1 has dimensions of energy because C1 plus C2 plus C3 is an energy. So C1 must have dimensions of energy. Very simple. Now I would like you to tell me the dimensions of this expression. Think about it. इसकी क्या dimensions हैं? तो मुझे बताइए, मोमेंटम है, वेवलेंथ है, वेव नंबर है, एनर्जी है, क्या डायमेंशन है इसके? एंगुलर मोमेंटम है, सॉरी वेवलेंथ, थोड़ा सा वेव नंबर, वेवलेंथ का इनवर्स, बिकॉज देखें 2me, देखिए ये एनर्जी है ना, 2me का अंडर रूट इज मोमेंटम, द लीनियर मोमेंटम. 2me is p squared. 2me over h bar squared is k squared. So this expression has dimensions of 1 over length squared. So let's write this as the square of a wave number. Let's write this as k x squared. देखो ये कांस्टेंट है, इस कांस्टेंट को हम अपनी मर्जी से जो मर्जी नाम दें. Let's call it kx squared, and k we know has to be a wave number, the inverse of the wavelength. ठीक है? So let's rewrite this expression as d square f over dx squared plus kx squared. F of x is 0, and we can solving this is child's play. The solution is fx is a dash exponent iota kx x plus b dash exponent minus iota kxx. So this is the solution. A dash and b dash are constants. Now we impose the boundary conditions. The first boundary condition is that at x equals 0, this function has to be equal to 0, which means that 0 equals a dash plus b dash, which means that b dash has to be equal to minus a dash. So this means that the function f of x equals a dash exponent iota kxx minus exponent minus iota kxx. ठीक है, क्योंकि b dash माइनस a dash के बराबर है. बाउंड्री कंडीशन अप्लाई की है. तो what is this? What is this function equal to? This is 2 iota a dash sine of kxx. So we can write this variable 2 iota a dash is just some constant. This is some constant, right? We can write this as a. Let's write this as a. हम इसको ना भी लिखें a के तौर पे. I'm just trying to simplify things. I can write this as a, as another constant a, which is imaginary. It could be imaginary, it could be real, depending whether a dash is imaginary or real. So this is just some constant a sine kxx. So this is f of x. Where kx is defined as 2m c1 under root divided by h bar. ठीक है, मैं कुछ नहीं कर रहा, मैं बस कदम ब कदम आगे चलता जा रहा हूँ, आहिस्ता आहिस्ता. कोई कंफ्यूजन नहीं होना चाहिए किसी भी स्टेज पर आपको. ठीक है, सो दिस इज द फंक्शन f of x. Likewise, without solving, without going through the exact same procedure, I can write the function g of y. What is g of y now? It is some constant b sine of ky y, where ky is defined as 2m c2 over h bar. Likewise, h of z is some other constant c sine of k zz, where kz is 2m c3 over h bar, and the additional constraint that c1 plus c2 plus c3 must be equal to E. अच्छा, अब देखिए boundary conditions. There are two kinds of walls in this cube. There are how many walls? 6 faces. There are 6 faces. 3 of those faces touch the origin, but 3 faces don't touch the origin. For example, this face doesn't touch the origin. This is at x equals L. This face is at x equals L. This face is at y equals L. This face is not touching the origin. So there are 2 kinds of boundary conditions, and here we have only applied one of the boundary conditions. What about the other boundary condition? What is the other boundary condition? The other boundary condition is that the function f at x equals L must equal 0. But the function at x equals L is given by a sine of kxl must equal 0, because now our function is this one. So insert the value of x equals L into this expression, we get the function at x equals L, and that has to be equal to 0. Now this imposes another constraint, and that, what is the constraint? It's a constraint on kx. And what is the constraint?
KXL equals n pi.
KXL the constraint is that KXL must equal n pi. Let's write a small x with n, nx pi. And what are the possible values of nx? What are the possible values of nx? 0, 1, 2, 3? 0 नहीं हो सकता, क्योंकि then the wave function will disappear, the particle does not exist. देखो मैथ्स और फिजिक्स दोनों हाथ जोड़ के चलती हैं. मैथ्स कहता है भाई अगर ये 0 भी हो तो कोई बात नहीं, लेकिन फिजिक्स कहती है 0 नहीं हो सकता, because then the wave function does not exist. So we're talking about a legitimate objective particle that does exist. So nx की minimum value 1 है. So nx can take up the value 1, 2, 3, which means nx can be a whole number. So you get this additional constraint on kx. So likewise you get a constraint on ky and a constraint on kz. Let me write all the constraints together here. kx L. In fact, kx is nx pi over L. Ky is n by pi over L, and kz is n z pi over L.